So first of all, I would like to say that I like it very much that I can see the audience. And however, I would like to apologize that I'm going to switch off my camera now because I sometimes experience some problems with my upload, and this is slowing down everything a bit. So as soon as I find the button, I switch off this now. Well, so I would like to thank, first of all, of course, the organizers for inviting me to this very interesting workshop. I will talk today on a question about a technical parameter in adaptive convergence or optimal adaptive convergence theory, and in particular on the Dörfler marking parameter. In fact, it can be shown that this marking parameter leads to optimal convergence rates whenever it is small enough, and the question is whether this is necessary or even a sharp bound. Okay, and in my talk, I only have two sections. In the first section, I will show you some framework which will allow me to precise the question I have just raised, and the second section I will partially answer that question, hopefully. Okay, well, let's start with the first section, and we will have a look at an abstract problem. So we have some initial triangulation T0, so that is, you may think about just a standard PDE setting. We have some initial mesh of, say, some domain omega, for example. We have a refinement routine that, given a mesh and some marked elements, puts out a mesh such that all marked elements, so that is the condition, all marked elements M are refined in the refined mesh. So you may think here, for example, in the context of PDEs, about newest vertex bisection or something in that direction. We will call this double T here the set of all refinements of T0 that can be constructed by our refinement routine. And here's some shorthand notation that we say that T hat is a refinement of T, then we denote this by T hat is greater or equal T. So that just comes from the fact that the refinement introduces some partial ordering, and this is the greater equal here in this sense. There's a technical condition which you won't see after that slide anymore, but this is a technical condition which is behind the optimality proof at some place, which says that a so-called overlay, which says that when we have two meshes, T and T star, then there exists a common refinement such that the common refinement, that's this T hat, of both the triangulations requires as much refinements as the sum of the both triangulations require, starting always, of course, from T0. Okay, having this triangulation framework and refinement framework available, our goal is to make an approximation error, which we call here delta, and which acts on the set of triangulations here. We want to make this approximation error small. So you may think of delta to be, for example, just, yeah, in the Poisson problem, it's just the H1 semi-norm, something like that, right? And then for adaptive finite element methods, for example, you have some finite element estimators available, and the finite element estimator or indicators is a mapping from the triangulation T into the non-negative real numbers, and its accumulation, so this is just accumulating all the indicators, is what we call our error estimator. Okay, so far so good. Now we have this setting available. One may ask a question, what is the optimal nonlinear approximation rate we can achieve. For example, say we can achieve the rate S here. That means that the infimum of our error quantity, the infimum over all triangulations with less or equal elements than n, vanishes like n to the minus s. Okay, so you have an optimal or nonlinear approximation rate S, which you can satisfy for the optimal sequence of meshes. So the question, of course, is that for practical algorithm, how to achieve such optimal rates by adaptive refinements. And one answer to that is you use an adaptive scheme with Dörfler marking. Okay, this goes in principle like this. So you have an iteration, and in each iteration you select some marked elements in your triangulation such that the error indicators on the marked set is the bulk of the total error, right, on the triangulation. And then in the next step you just refine the marked elements. So I used here the phrase almost minimal, and by almost minimal I mean that the set MK is almost minimal, but in cardinality among all meshes M that satisfy the Dörfler condition. Okay, so the minimal set is only a fixed constant smaller than the number of our marked elements. We can avoid this condition, but then the proof is getting more difficult, and I decided for the presentation that I stick to this version here. Okay, and now we recall some assumptions or axioms from a 2014 paper by Carstensen, Feischl, Page, and Pretorius, who kind of extracted from the optimal adaptivity proofs the conditions that were required to prove the optimal convergence rates. I kind of condensed it a bit to our needs, so it's not the full generality, but I think you will identify it with the original axioms. So the first one, A1, is the stability, which means that the error estimator, the error indicators on the, so this is the intersection of the two of T and its refinement, so that are the non-refined elements. So this can be bounded by the error, and the error here is measured, it's a square root, so this is a definition, this is just the square root of the error on the coarse mesh minus the error on the fine mesh. When you think of the H1 semi-norm, this would read like this. You have grad U minus grad U T squared minus grad U minus grad U T hat squared, and this equals by Pythagoras to grad U T minus grad U T hat. Okay, so and then you take the square root of this expression, of course. Okay, then we have as a second assumption the so-called reduction, and this means that there exists a reduction factor, which is the rho here, and on each refined element you reduce the indicator by a fixed factor of rho. Yeah. Okay, this just comes in PDEs from mesh size reduction, for example. Then you have a third assumption here, and this means that we have discrete reliability. So the error between two discrete solutions, so you see that should respect the error between discrete situations, say, is bounded by a fixed constant, call it capital lambda, times the error estimator only on the elements that need to refine to be refined when going from T to T hat. Okay, and then there's a fourth assumption which is satisfied by construction in our situation, because here this is an orthogonality assumption when looking at this definition here and taking the square, then it's obvious that you get this just by a telescopic sum argument, right? Okay. In addition to this four assumption, we need another assumption on the refinement procedure, which basically says that when we mark elements, then the effect that refining all these elements is of the size of the number of elements, right? So that is kind of a stability estimate for refinement, say. And then in this paper by Carsten, Feischl, Page, and Pretorius, they prove that in this situation, the error estimator vanishes with optimal rate, provided that the marking parameter is below a certain threshold, and this situation is 0 in between 0 and 1 divided by 1 plus lambda, and lambda was the constant in the discrete reliability, right? In the first paper on optimal convergence rate by Stevenson, there was another assumption involved, or property involved, and namely it was used the efficiency of the estimator, saying that the estimator is bounding also the error from below by a constant which we call small lambda here. And in this situation, you can prove that you have optimal convergence rates provided that the theta is in between 0 and little lambda divided by capital lambda. So I don't want to make a competition in between the two thresholds. I think there are situations where the one is better than the other one. I'll just state both of them, because the second one, in our particular situation, the second one is the sharper one, and that's why we are competing with this one. Okay. So now in our particular situation, we see in a minute that the lambda is 1, and then you see immediately that this is the better constant here. Okay, anyway. Okay, now of course there is the question whether this threshold is sharp or not, and this question basically was already raised in this paper by Carsten, Feischl, Page, and Pretorius, where you can find the statement that in principle that their proof is without the efficiency. This might be a first step, you can read this here, to the mathematical understanding of the empirical observation that each adaptive parameter between 0 and 0.5 yields optimal convergence rates. When I was reading this first, I was thinking, well, I don't know if this is true, and I was asking people, and I got the answer. Sometimes I got the answer, well, I don't believe, or I believe. Some people showed me examples, but in each of these examples, it always turned out that at the end, either it didn't fit in the framework, or that was some pre-asymptotics which happened there. So I didn't know. I also let some master student compute some toy example with some anisotropic diffusion, and because we wanted to break the efficiency index a bit. And it turned out that, well, after fixing the marking strategy in Alberta, it turned out that indeed we got optimal convergence rate for theta being, I don't know, 0.99 or something like that. Okay, so even much bigger than 0.5. So we didn't kind of manage to find a counter example, and so we decided to construct one, and this is the example now I will present you in the second section. So the example is a 1D example, and the reason that is 1D is because that you don't need to care about hanging nodes and all this stuff which is really causing problems when you try to trace all the stuff, what is happening during all the refinements. So we take omega to be the interval from 0 to m, you can see it here, yeah. And we have initial refinement, initial triangulation, which is just all the unit intervals you can see here. Okay, from 1 to m. The refinement is just taking one element and replacing it by the two children. Okay, so you can see it here. I've replaced this element by the two children. Again here, and again here, for example, right? You see immediately that you take one element out and put two elements in. So whenever you mark an element, you increase the number of elements in the triangulation by 1. So we have perfectly satisfied this bound, the stability for the refinement, say. And in addition, I would like to introduce here also some common notation in refinement, the generation of an element. Okay, if an element is in the initial triangulation, I say that it has generation 0. If I refine it, then then you have generation +1. Okay, so the children have generation of the parents +1. Okay, and now we come to the error estimator, or error and slash estimator, say. So we fix an alpha bigger than 0, so that is arbitrarily fixed. And we define the error estimator by that. So first of all, we take here exponential decay to the minus alpha and the generation of the element t, whenever t is in the interval between 1 and m. Okay, so whenever here you can see it, whenever you are in this region. And here also is a exponential decay, but this is not depending on t, but on the triangulation and G0 of the triangulation, and this is defined here. This is just the generation of the element containing 0. Okay, so this guy. And if I'm taking the element that contains 0, I define the error indicator just by 1 over m minus 1 times the error indicator, or the accumulated indicator on this whole interval here. And on all other elements, so these two, for example, I just define the error indicator to be 0. Okay, so first observation, one moment, the error is then defined to just equal the error estimator. And in this situation, we have, of course, efficiency with constant 1, okay? Well, and the first observation here is that we even can establish exponential convergence here. So if we always take the element that contains 0, then, seeing this, only this is reduced by an exponential decay. So you get, so this is the factor m of the error estimate on the initial grid. It's m, one can prove that it's m. And this is the decay that comes from this factor. And of course, then tk, the number of elements in tk is just m plus k, as m from the initial triangulation, and then all refinements. You only refine once per iteration. And the generation of the G0 of tk is k then, and then you can replace this by k, and you see you have exponential convergence rate. So you can satisfy any algebraic convergence rate you want to have on the optimal sequence of refinements. Okay, now let's check our assumptions. So here is just in a condensed way, written the definition of the error indicator. By definition, we basically have the efficiency of the indicator, so lambda the small lambda equals to 1. The reduction can be satisfied. Well, I mean, you can see it here. When you define the initial element, then you have this reduction factor here, so 2 to the minus alpha divided by 2. And when you refine any other element, you have also this reduction factor. So you have the reduction on the refined elements by a factor rho, which is 2 to the minus alpha divided by 2. We also can prove discrete reliability. So here we have two situations. So first of all, we assume that T0 is refined. So T0 is in T and not in without T hat. So that means it is refined. You write down this discrete arrow between the two meshes. You can just write it like this. You can simply skip that. And you get here the error estimator. And this error estimator is just m times the error estimator on the initial element. And this then obviously can bounded by that guy here. Okay, so in this situation, you get lambda for the discrete reliability to be capital M. And also, when T0 is not refined, then just by canceling the not refined elements, you get this property here. And again, you can skip this and you end up with that. Okay. So in this case, you even have discrete reliability with constant 1. Another comment here, you have monotonicity also on the non-refined elements. And then this is a property I also need and mentioned previously. When introducing the error, we need monotonicity on the error. Okay, now optimal rates. In this case, so in our case, so in our example, we have the thresholds. This is the threshold from the Stevenson paper, and this is the threshold from the axioms paper. So they're slightly different, but in our case, this is the sharper threshold. So we go with that. So that is the result by Rob. Whenever the theta is in between 0 and 1 over m, we can satisfy any rate s. Because we have exponential convergence, we can satisfy any rate s. So fix the rate s. This is true, of course, then possibly for different constants, but you can prove that. Well, indeed, when refining always only the element that contains 0, okay, you can even construct that, yeah, then that is by definition you have that the element on that contains 0, the indicator is by definition this guy here, and this implies that you just get that the indicator on the 0 element is 1 over m times the whole estimator, and this is exactly the Dörfler condition, right? So, and for this refinement, we have seen the exponential decay. Okay, well, so now let's see what is happening when we violate the threshold condition. And in this situation, we simply choose theta to be 1 plus gamma divided by m, with a gamma greater than 0. And well, I also assume that gamma is less than 1 here, okay, or less or equal 1, say. Yeah, in this situation, we proceed like this here. So we start from the initial triangulation. That is the initial triangulation, of course. In this situation, you have the indicator in the first interval is 1, and we choose M0, so the first marked elements, to be the first interval and the second interval. Okay, we cannot just choose the first interval because this is not satisfying Dörfler condition anymore with that parameter, and so we have to choose 2. Okay, then we refine, we get this guy here, and in the second iteration, we choose for the marked elements again the first interval, and then the next unit interval in the triangulation. Okay, and then we iterate this until we went once through the whole domain from left to right, right? So in this case, the first element, so the element 0, 1, is refined m-1 times, but only towards the origin, and all other elements are fully refined once. Okay, and now we enter the next iteration, and we can generalize this. And what we do is we always take the initial element, so not the initial element, the element containing 0, and then we take all elements in the whole unit interval. Okay, we do not need to take all of these elements, but I will show you in a minute that this anyway provides us with almost optimal marking sets. So in this situation, after L times m-1 refinements, the first element is refined L times m-1 times only towards the origin, and all other elements are fully refined L times. Okay. So now check the almost optimal cardinality of the marking strategy. So first of all, in each step, we mark 2 over m times our whole indicator. And this is greater or equal, of course, 1 plus gamma, because I said before that gamma is less or equal 1. Well, in each iteration, and now that's basically the trick here, in each iteration, so if you have such a unit interval, you need to at least mark gamma divided by 2 to the minus alpha portion of this interval, okay? And so you can, because you have a uniform refinement of the whole interval, you can mark the whole interval and only increase the number of marked elements by a fixed factor of, here you can say it, of at most 2 to the power of alpha. I think that's a sign mistake, there's a plus here. 2 to the power alpha divided by gamma. Okay, so that's the trick why you get quasi-optimal or almost optimal Dörfler marking here. Okay, now let's have a look at the convergence rate, and it's straightforward to prove that the error estimator behaves like 2 to the minus alpha times ml times m, and we only look. We finish all these m-1 iterations and have this, you know what I mean. So you go one through the whole domain, a second one, and we go L times through the whole domain. And once we have finished this, you can always show that the error estimator behaves like this. Okay, so that is on this subsequence, say with L, that is the behavior here. And for the number of elements, you can prove that once you have finished one of these loop through the whole domain, so you go from m-1 times L to m-1 times L-1, you have m-1 refinements for the initial for the element containing 0 plus 2 times all the other elements. Okay, and now you can iterate this, and you get the potential factor 2 to the power of L times m here. Now, if we have a look at the convergence rate, you can simply put in this here, and then you can take this power minus alpha m out, and you see here that's exactly an upper bound for the number of elements here, and you can replace it by the number of elements here, and you see that you can, for the error estimator, at most achieve a convergence rate of alpha times m. And we have seen that this is suboptimal because the optimal convergence rate is, well, exponential. Okay, and this is the end of the talk. Basically, let me conclude and remark on our results. So, first of all, what this example proves is that the threshold condition is sharp in general within the framework of the axioms. Okay, you cannot avoid it as long as you stick to this abstract framework. For every marking parameter, you can construct an example such that some quasi-optimal Dörfler marking produces suboptimal rates. And even the result can basically be general, so to optimal Dörfler marking. So you really take a minimal Dörfler marking set, but then the analysis is getting more cumbersome. But if you're interested, you can, of course, visit our paper on that. So the question, of course, is what's about this statement in general cases? And I have to say I don't have an answer. There might be for partial differential equations that there is indeed some more stuff in behind that you can always say see this rate, or maybe I was just not reported an example that it was telling, well, no, you cannot see this rate for any marking parameter theta. So I don't have a complete answer to that. The only thing I can say is, as long as you can stick, as you stick to these axioms, there is no chance to prove it. So either you have to extend this or even go to a different framework. By the way, when you go for maximum marking, the maximum marking strategy, independent on the parameter of the maximum marking strategy, will eventually pick up only the element that contains zeros, and so eventually you get a exponential convergence rate, and so this would satisfy optimality here. Okay, and with that, I would like to thank you for your attention, and these are just a small list of papers I've mentioned during the talk.